Hello? 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 Let's see. 헤드폰 스피커는 헤드폰 출력 정지. 음향기기 볼륨 믹서. Hello? 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 Wait a sec. Can you hear me? Write something, anything in the chat. Can you hear me? No? Okay, thank you. Thank you. Share screen. Let's see. Okay, in 3 minutes. Are you in the classroom, or anywhere in the campus or dormitory, your room? Let me ask. Let me ask my, oh my goodness. Okay, we have only 20 to 0. Where are the rest of the classmates? Please call them, invite them to this live streaming. I have to do the lecture. Okay, 30. I think we have 40, 45. Where are the rest of classmates? Okay, some of you in the room or dormitory, it doesn't matter, but you must uh, watch this and change your name Korean instead of English, whatever alphabet, because the teaching assistant count you and say something, anything, write something, anything in the chat room. I think can you? How do we know you are here? Mm. Type anything, something. I don't know how to count you are here. Yes, that's good idea. 장한별. Uh, right, 28. What? Why? Number is decreasing. Okay. Is it? Is it all? We have only 26. If you are sitting in the classroom, maybe teaching assistant turn on the YouTube live streaming to the screen. Uh, Thank you, Now I understand why people uh, do something live streaming and shout and smiling, laughing, watching the heart. Okay. Here is announcement. Midterm exam. Okay. April 15. It's Tuesday. Yes. From 13 to 15, 2 hours. I think you can solve all the questions within 2 hours. Maybe 1 hour would be enough, but I would like to give you enough time to solve the questions. But the venue, place is not the same place as like the lecture room. It's not L21. It's E7241. Don't forget it. Okay, E7241. General lecture room. Okay, and coverage, midterm coverage, chapter 1 through 7. Okay, so we have to run to finish chapter 7. Okay, so we have done activity series and hydrogen. So you don't need to memorize this table, but this table is very important. Where is the Very important. And what else? I have sent this information through email, so don't forget it. And today we start metal and acid displacement, displacement reactions. So when you add copper into the aqueous solution, silver nitrate, then mm, there is replacement reactions. Copper and silver replaced. Okay, so elements higher on the activity series are more reactive. Elements higher on the activity series. This is the activity series of metals in aqueous solution. Where is copper? Copper. Copper here. Where is silver? Silver here. So copper is above the silver. So as you see here, copper replaces silver. And the final product is copper nitrate plus silver metal. So I told you before, you have to imagine, think what happened on the surface of metals or chemical reactions on the surface. Mm, so copper, let's see. Yes, silver nitrate dissolved into the aqueous solution, ionized. So silver ion and nitrate ion dissolved, dissociate into this aqueous solution, right? And then this silver is positive. When it is near to the copper surface, copper has a lot of electrons, and these silver plus take electrons from copper and what reduced. So as many as silver reduced on the surface of copper, it has a bulky shape of silver bulk metals. So we can write silver S, 2S, and copper nitrate. And copper is a copper of elemental copper comes from the surface, and it is oxidized to copper 2 plus. Copper 2 plus. So the element below will exist as the element. Okay. So this is the displacement reaction. Molality is important, very important. The quantity of solute, the quantity, gram or mole, okay? Quantity of solute in a solution, liter, can matter to a chemist. Can matter to chemists. It is important to chemists. Quantity of solute in a solution. We call the amount of dissolved its concentration. Its concentration is molality. Molality is one way to measure the concentration of a solution. One way to measure the concentration of a solution. So the equation is very simple, but don't forget it. Molality, large M, equal moles of solute, moles of solute over volume of solution in liters, okay, mole per liter. Molality can be used as a conversion factor between moles and liters. So it is very useful. Okay, molality can be used as a conversion factor between moles and liters. Mixing solution. Let's try to mix something to dilute into aqueous solution. To create a solution of a known molality, weigh weigh out a known mass of the solute. So weigh out 39.9 gram of copper sulfate, and then add solute to a volumetric flask. Add solute, this copper sulfate, into the flask. Volume volumetric volume volumetric flask, and add solvent to the line. There must be a line here, around here, line on the neck of the flask. Mm. You must keep this sequence, okay? Do not uh, add solution add solvent first. Add solute first, and then second solvent. Then you can make a very precise uh, concentration of solution, right? Add water until solution just reaches calibration mark. We call this calibration mark. Just 1 liter. It looks like 1 liter or 500 milliliter. Uh, on neck of flask and swirl to mix. Then you can make mm, concentration of solution. Dilution. A solution can be diluted by adding only solvent. Okay, you just add the solvent to dilute the original solution. The concentration is lower. Of course, concentration is lower, but the moles doesn't change. Moles doesn't change. This is the definition of dilution. Okay, so draw 25 milliliter of 1 mole stock solution into pipettes. So we made it. Okay, we made it, and just to draw 25 ml of this stock solution and add this concentrated solution in pipette to 250 ml volumetric flask. Dilute with water until solution reaches calibration mark here, calibration mark on neck of flask, and mix create 0.1 mole solution. So this is the experimental way to dilute the solution. So there is simple relation between the volume and concentration. The molality of a new solution can be determined from this equation. MCVC equal MDVD. Memorize it. It's important. Well, MC and D are the molality of the concentrated and dilute solutions. Concentrated, dilute solutions molality, respectively. And volume, C, concentrated and diluted volumes of the two solutions. So if you multiply molality times volume, then you can get moles. Stoichiometry applied to solution. Mass of substance A, use molar mass of A, moles of substance A. So you can change mass to moles, right? And then use coefficients from balanced equation. You have to memorize the simple chemical reactions, balanced chemical reactions. I may give the basic chemical reactions, but sometimes the question doesn't have the chemical reactions in the question. In that case, you may have to write the starting point of the solution is writing the balanced chemical reaction equation first, and then try to solve the question. Moles of substance B by using this coefficient use coefficients from valence equations. Then you can calculate molality of solid solution containing substance B or volume of solution containing substance B. They are all relationships in between A and B in the chemical balance equations. Okay, we do the examples later. Titration. Titration is important. Titration. I think you may do this experiment in the general chemistry experimental class. Uh, Titration is an analytical technique. This is a technique in which one can calculate concentration of a solute in solution. Okay? You can decide, identify the unknown uh, concentration. So let's see, 20 ml of acid solution added to flask, and then a few drops of acid base indicator added to flask, and standard sodium hydroxide solution added to flask from burette. This is burette. Uh, Burette has this cork. You can control the drop-wise uh, sodium hydroxide solution into the flask, right? Burette has this cork switch. Solution becomes basic on passing equivalent point, equivalent point, equivalent, equivalent point triggering indicator color change. So you can change transparent solution to what purple color final volume. Then you can read the final volume reading. Okay, and then calculate the concentration of unknown things. So this is the way how to use this technique, titration. Volume of standard solution. Volume of standard solution need to reach equivalent point. Use molality of standard solution. We must know the molality. And moles of solute in standard solution. Use coefficients from valence equation always. Then you can calculate moles of solute in unknown solution. And then use volume of unknown solution. We measured by burette, right? Then you know the concentration, molality of unknown solution. A solution of known concentration called standard solution. Standard solution. Don't forget it. Standard solution. Known concentration is used to determine the unknown concentration of another solution. The reaction is complete at the equivalent point, which is based on the scene and the point. So you can see the color change. We use this type of titration in the gas phase reaction also. Okay. Um, oops. Yes, this is the end of the chapter 4. Right. This is the end of chapter 4. Then we'll. Okay. And how many? 37. Okay. Many of us came back to the class. Thank you. Is it? I'm going to. We have to do some exercise. Busy today. I'm in San Diego, California. It's a bit cold. This is the end of the winter. I love Southern California. The very very nice place to live. Have you been to Southern California, San Diego, Irvine, LA? There are many South Korean in Irvine and LA, and many good universities: UCLA, Caltech, UC San Diego, UC Irvine, uh, all those UC Santa Barbara, all those California State universities are very highly qualified and good. So later on, UC Berkeley is not a Southern California. Mm. SoCal. So in short, we call Southern California it's SoCal, SoCal, SoCal. Uh, Southern California is a very very nice place to live. Um, the air is very dry, so under a hot weather, even in the summer, middle of the summer, it's not high humidity. So let's see, where is it? Let's see, Ch3. Right. Um, Again, let's do some exercise of chapter 3. Are you ready? Uh, I'll give you some time to let's let's consider sample exercise 3.1: interpreting and interpreting and balancing chemical equations. The following diagram, you can see the diagram here. The following diagram represents a chemical reaction in which the red spheres are oxygen atoms. Red spheres are oxygen atoms. Red are oxygen atoms, and the blue spheres are nitrogen. Okay. A. Write the chemical formula for the reactants and products. What is the reactant? This is reactants, and this is products, right? A. Write the chemical formulas for the reactants and products. B. Write a balanced equation for the reaction. Okay. C. Is the diagram consistent with the law of conservation of mass? What is the law of conservation of mass? We have to think about that. So, how to solve this question? A. The left box, which represents reactants. This is the reactants. Contains two kinds of molecules. Can you see? One and two, two kinds of molecules. Those composed of two oxygen atoms. Where is it? Two oxygen atoms. Molecular oxygen. And those composed of one nitrogen atoms. Where is it? One nitrogen atom. One nitrogen atom and one oxygen atom. This is NO. This is NO, right? This NO. So we have molecular oxygen and nitrogen monoxide in the right box. The right box, no, sorry, left box. The right box here, product, right box, which represents products, contains only one kind of molecule, which is composed of one nitrogen atom, two oxygen. This one nitrogen, blue sphere, two red spheres, two oxygen, NO2, nitrogen dioxide. So right, we solved the question. Chemical formulas for the reactants and products. B. Unbalanced chemical equations. From the left box, we can write molecular oxygen and nitrogen monoxide. Uh, uh, Under a chemical reaction, it changed to NO2. Okay, it's unbalanced. So An inventory of atoms on each side of the equation shows that there are one nitrogen and three oxygen. One, two, two, three. Okay, three oxygen on the left side of the arrow. Uh, left side of the arrow, three oxygen, one nitrogen, and one nitrogen, two oxygen on the right side. To balance oxygen, we must increase the number of oxygen atoms on the right while keeping the coefficient of NO and NO2 equal. I see. So, uh, well, simply just add coefficient 2 here, okay, as like this. And then oops, uh, another 2 right here. Uh, then we can make 2 nitrogen and 4 oxygen left side of the arrow and 2 nitrogen, 4 oxygen right side of the arrow. It is balanced, right? And then 3, C, the reactants box contains 4 oxygen and 8 nitrogen monoxide. So the molecular ratio is only 1 oxygen for 1 molecular oxygen for each 2 nitrogen monoxide as required by the balanced equation. Okay, so the products box contains 8 NO2, which means the number of NO2 product molecules equals the number of NO reactant molecules, as the balanced equation requires. There are eight nitrogen atoms in the 8 NO molecules in the reactant box. There are also 4 times 2, 8 oxygen atoms in the oxygen molecules, blah blah blah. In the products box, we find 8 NO2 molecules, which contains 8 nitrogen atoms, and NO2 molecules, which contains 8 nitrogen atoms, and 8 times 2, 16 oxygen atoms. Drawing is consistent with the law of conservation of mass. Well, let's check it. Let's check it. All of the oxygen, molecular oxygen, and nitrogen monoxide completely react each other, and uh, nothing left unreacted molecules, elements. So this reaction is consistent with the law of conservation of mass. Yes. Okay. Good. Uh, let's figure out the 3.2. Balance the equation. Look at this. Sodium and water. We add water into the sodium. Then what happened? It became sodium hydroxide aqueous solution, and hydrogen gas comes out. So do it. Begin by counting each kind of atoms. Let's count one sodium, uh, one oxygen, three hydrogen. It's different, right? Okay. Uh, Two sides of the arrow. There are one sodium, one oxygen, and two hydrogen on the left side, and one sodium and one oxygen, three hydrogen on the right. The sodium and oxygen atoms are balanced, but the number of hydrogen atoms is not. To increase the number of hydrogen atoms on the left, let's try to place in coefficient 2 here. 2. Then what else? In front of the water. Then still something strange. Then adding coefficient 2 in front of the sodium hydroxide here. Right. And then balance H in this way, uh, brings oxygen into balance. So we need uh, more sodium. So write another 2 here. Uh, we now have 2 sodium atoms and four hydrogens. 4 hydrogens each side, and 2 oxygen, 2 oxygen, 2 oxygen. So the equation is balanced. Okay, it's not difficult. You can do it. Let's go on. 3.3. Write a balanced equation for the combination reaction between lithium. What's the oxidation number? Lithium metal and fluorine gas. B, the decomposition reaction that occurs when solid barium is heated. Two products formed, a solid and a gas. Okay, let's do A. Balanced equation. With the exception of mercury, all metals are solids at room temperature. Fluorine occurs as a diatomic molecule. F2, diatomic molecule. Okay. Uh, mm, Thus, reactants are lithium, solid metal, and fluorine gas. The product will be composed of a metal and nonmetal, metal and nonmetal. So we expect it to be an ionic solid. Yes, it looks like ionic solid. Lithium ions have a +1 charge. It's like this. Lithium plus, whereas fluorine ion have -1 charge. Fluorine minus. Thus, the chemical formula for the product is lithium fluoride. The balanced chemical equation is this. All right. When you use fluorine gas or hydrofluoric acid, HF is a very, very, very strong acid. So uh, I think you cannot use this acid in the lab, in general lab. And you have a special license to use this one. This is very strong and very strong. So don't touch it. Don't touch it. And the chemical formula of barium carbonate. Barium carbonate. And barium carbonate decomposed to form, no, not that this one. We expect barium carbonate to decompose barium oxide and CO2. Barium and calcium are both in group 2A in the periodic table. So further suggest they react this. The decomposition reaction. This is combination reaction. This is combination reaction. This is decomposition reaction. Decomposition reaction. Barium oxide. Solid. And 3.4. Write the balance equation for the reaction that occurs when methanol is burned in air. Methanol. Let's burn the methanol. Let's see. We have methanol here. And in order to burn this methanol, we need oxygen, of course. And then most of the hydrocarbons should change to carbon dioxide gas, and then the rest of them should be water. So this is basic equation, unbalanced equation. So the carbon atoms are balanced. There is one carbon each side, and one each side of arrow, because methanol has 4 H atoms. How many? 1, 2, 3, 4. 4 hydrogen atoms. We place the coefficient 2 here. Coefficient 2 here, like this. In front of water to balance the hydrogen atoms. Adding this coefficient balance hydrogen but gives 4 oxygen atoms in the product. So we divide this, no, not divide. Uh, we can place coefficient 3 over 2 uh, here in front of the oxygen to give 4 oxygen atoms in the reactants. So to simplify this, we multiply 2 in both sides of the arrow. Then we can get this one. Beautiful. Okay, there are practice exercise, you do that. And 3.5, calculate the formula weight of glucose, sucrose, table sugar, sucrose, and calcium nitrate. Formula weight, not difficult. Just by adding atomic weights of the atoms in sucrose, okay, we can find 342.0 AMU. B, if a chemical formula has parentheses as like this, bra and parentheses, the subscript outside this one, 2, the parenthesis is multiplier for all atoms inside. Thus, okay, 2 nitrogen, 6 oxygen, and 1 calcium. So, 164.1 AMU. Good. 3.6. Calculate the percentage of carbon, hydrogen, and oxygen by mass in glucose, sucrose. Is it sucrose? Yes. Table sugar, sucrose. Let's start. Okay. We have calculated the molecular weight, AMU, of this sucrose. It should be here. And then carbon has 12 AMU and 1 AMU, hydrogen, and number of elements in front of this relative existence. Then we can make the percentage carbon. Then it has times 100, it has 42.1%, 6.4%, 51.5%. 12 carbon, 22 hydrogen, 11 oxygen. Okay. And our calculated percentage must add up 100. Okay, after the solution, you have to find that this is 100%. 3.7. Without using a calculator, arrange these samples in order of increasing number of carbon atoms. Increasing number of carbon atoms. Let's see, 12 grams of 12 carbon. And 1 mole ethane. Sorry, 1 mole of ethane, C2H2, and 9 times 10 to the 23 molecules of CO2. So 1 mole of defined as the amount of matter that contains as many units of matter as there are carbon atoms in. Exactly, memorize it, 12 grams of 12 carbon. Okay, thus 12 grams of 12 carbon contains 1 mole of carbon atoms equals 6.2 times 10 to the 23 carbon atoms. Memorize it. It is very important. Okay? Exactly. Memorize it. So it has 6.202 times 10 to the 23 carbon atoms. Let's say 1 mole C2H2. 1 mole of C2H2 contains 6.02 times to the 23 C2H2 molecules, right? Uh, so simply, uh, you have 2 carbons in this molecule. So multiply 2 to this, then you can get 12.04 times the 2 10 to the 23 carbon atoms, right? Lovely. Because each CO2 molecule contains 1 carbon, okay, the CO2 samples contains 9 times 10 to the 23 carbon atoms. If this is the number of molecules, each molecule has 1 carbon, so it's same number of carbon atoms. So this is the answer. The order of increasing numbers of carbon is this. Uh, the smallest one is this one, 6 times 10 to the 23 carbon, and 9 times 10 to the 23 CO2, and then 1 mole of ethane. Right? Good. 7.8, 3.8. I want to drink some water. Let's calculate the number of hydrogen atoms in 0.35 mole of glucose. Let's see. Avogadro's number provides the conversion factor between number of moles of glucose and number of molecules. So you know this concept, right? You know this concept. So how to solve? We need to find how many hydrogen atoms. So we have 0.35 mole glucose times, what is this? 1 mole glucose is 6.2 times 10 to the 23 molecules. Okay, 1 molecule. This is conversion factor. And then how many hydrogens in 1 molecule? 12 molecules hydrogen in this molecule. So this is all what we want. And then delete, delete, and delete, and this one, and this one, and this one. We can get this. Okay, 2.53 times 10 to the 24 hydrogen atoms in this 0.35 mole of glucose, right? And next, what is molar mass of glucose? Molar mass. Okay, molar mass. Our first step is to determine the formula weight of glucose. Formula weight. Let's measure the formula weight. How many carbons? 6 carbons. Then 6 times 12 AMU. And 12 hydrogens. 12 times 1 AMU. And 6 oxygen. 6 times 16 AMU. Then so we have 180 AMU. This is molar mass. Molar mass. Because glucose has a formula weight of 180 AMU, 1 mole of substance has mass of 180 gram. Has molar mass gram per mole. Well, actually, AMU is same as gram per mole. Molar mass gram per mole, same. Another meaning of AMU is gram per mole. Okay, what did we miss? Okay. Next, 3.10. Calculate the number of moles of glucose in 5.380 gram sample. Number of moles, how do we figure it out? That's using 1 mole of glucose equal 180 gram by the definition. To write the appropriate conversion factor, we have 5.380 gram glucose here, and 1 mole equal 180 gram, right? Uh, this is conversion factor. You can delete gram, right? Then this is, let's divide this number by 180. We can get this, right? Lovely. Okay, another one. Calculate the mass in grams of 0.433 mole of calcium nitrate. Mass in grams mole. Calcium nitrate. First, let's write what's calcium nitrate. CaNO3 2. Because the calcium ion is Ca2 plus and nitrate ion NO3 minus, the chemical formula of calcium nitrate is this. Adding the number weights of elements in the compound gives a formula weight 164.1 AMU. Okay, 16. So we just multiply this because it has mole, 0.433 mole, multiply this conversion factor, then we can get this gram of calcium nitrate, right? This is what this question wants. Okay, next. How many glucose molecules are in 5.23 gram of glucose? B. How many oxygen atoms are in this sample? Right. How many glucose molecules? Then what should we do? First, convert gram to mole, right? So we have 5.23 gram glucose. Then you know this 1 over 180 gram mole per gram, this conversion factor. We used it in the previous questions. And then 1 mole is, by the definition, 1 mole is 6.02 times 10 to the 23 molecules, right? So delete, and then multiply all of this. We can get 1.75 times 10 to the 22 molecules, right? B, oxygen atom. In these molecules, 1.75 10 to the 22 molecules, how many oxygens? 6 oxygens in these molecules. We have this conversion factor. So you just multiply 6 to here, then you can get this one. Okay. Add one more 0 here, 23. Good. Ascorbic acid, vitamin C, contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. What is empirical formula of ascorbic acid? In this question, you have to assume 100 gram of vitamin C. That might be starting point, as see here. For simplicity, we assume we have exactly 100 gram of material, okay? Although any other mass could also be used, but for simplicity. Assume 100 gram sample, gram of each element, use molar mass of, okay? So we change this to gram. Okay, gram. And then next we calculate the numbers of moles of each element. We use atomic masses with 4 significant figures to match the precision of our experimental masses. As like this. Okay, one more carbon, 12 gram, right? Uh, gram per mole. You can use this converting factor. Hydrogen, there is typo. This is hydrogen. Okay, this is hydrogen. Correct it. No, you don't need to correct it. This is typo. And 4.45 mole H. Maybe textbook may be wrong. 54 divided by 16, then 3.4 mole oxygen. What was the question? What is the empirical formula? We have to write the empirical formula. Then you have to divide all the numbers by the smallest number of moles. So let's divide 3.4.407 by this. Then it's almost approximately 1. It's almost 1.3 and 1. Okay. Then you can see the ratio of hydrogen is too far from 1 to attribute the difference to experimental error. In fact, it is quite close to 1/3. This suggests we should multiply the ratio by 3 to obtain whole number. Let's multiply 3. Then we can get this whole number. Then the empirical formula is C3H4O3. Beautiful. Okay, another example exercise. Mescaline, a hydrocarbon found in crude oil, has an empirical formula of C3H4 and an experimentally determined molecular weight of 121 AMU, gram per mole. Right? What is its molecular formula? Right. Then first we have to use this one, right? And then find the whole number. The formula weight of empirical formula is this, and the total molecular weight is 40 AMU, right? And then experimentally we determined molecular weight 120, right? So we divide this by 40, then we can get 3.03. Then we multiply this number to the empirical formula, right? Then you can get C9H12, right? So use whole number ratios make physical sense because molecules contain whole number, because molecules contain whole numbers, right? Could result from small experimental error in the molecular weight. Right. Next question. What's the next question? Isopropyl alcohol, sold as rubbing alcohol, is composed of carbon, hydrogen, and oxygen. Combustion of 0.255 gram of isopropyl alcohol produces 0.561 gram of carbon dioxide and water. Determine the empirical formula of hydropropyl alcohol. We know many information. Right? So we use those information. Let's change the gram to moles, right? So because all of the carbon in the sample is converted to carbon dioxide, we can use dimensional analysis and follow the steps to calculate the mass carbon in the sample. Mass CO2 produced, uh, molar mass CO2, 44 gram per mole, right? This is conversion factor. So we are going to use this gram of carbon dioxide right here, and 1 mole CO2 equal 44 gram of CO2 exactly, and 1 more carbon equal 1 more CO2, and 1 more carbon is 12 gram of carbon, so we can get 0.153 gram carbon only atom. Okay, uh, grams carbon we calculated. Grams carbon. We have to determine the empirical formula. Okay, so we need grams carbon, and then what? Uh, grams hydrogen. Grams hydrogen. We know 0.306 grams water. Okay, then we have to multiply 1 mole water over 18 gram mole of water. So the conversion factor, and 2 hydrogen over 1 mole water, and 1.10 gram hydrogen equal 1 mole. So multiply all of this, then delete, and then you can get this one, 0.0343 gram hydrogen. The mass of sample is 0.255 gram. The sum of the mass of carbon, hydrogen, and oxygen. But we must know the mass of oxygen, right? So we simply mass of sample minus uh, the summation of carbon and hydrogen. So this is the gram of oxygen. And then the number of moles of carbon, hydrogen, oxygen in the sample is this. So we calculated this, and this. So multiply the mole per gram of carbon each element. Then we can get mole, carbon, hydrogen, and oxygen, right? And then we divide each moles by the smallest number. And then we can get 7.91. The first two numbers are very close to the whole number 3 and 8, giving the empirical formula this C3H8O. Lovely. It looks complicated, long steps, but I think if you practice this step by step, you can follow, right? Try to do this. Right. Okay. Right. Determine the how many grams. Exercise 3.16. Determine how many grams of water are produced in the oxidation of 1 gram of glucose. Determine how many grams of water these are produced in the oxidation of 1 gram of glucose. 1 gram of glucose. Let's use the stoichiometry, and then relationships. So first we convert gram of glucose to moles, right? Always. 1 gram of glucose times 1 mole, 180. Then you can get, here is another typo. 6 here. And next, we convert moles of glucose to moles of water using the stoichiometric relationship. 1 glucose to 6 mole water. So moles of water equal 1 gram of glucose and 180, 1 over 180, and 6 mole water is 1 mole of glucose. And finally, we multiply 18 gram water and 1 mole hydrogen. Then you can get 0.6 gram water. What do we do next? Second, what was the question? How many grams of water? How many grams water? 0.6 grams of water, right? Okay, and then 17. Solid lithium hydroxide. Solid lithium hydroxide is used in space vehicles to remove carbon dioxide gas exhaled by astronauts. The hydroxide reacts with carbon dioxide to form solid lithium carbonate and lithium water, liquid water. How many grams of carbon dioxide can be absorbed by 1 gram of lithium hydroxide? Recently, there is, I think, last few days, there are big wildfires. You've seen the news, okay? So firefighters use oxygen tank, but most of the case, firefighters can use oxygen tank within 30 minutes. Do you think it's possible to extinguish wildfires within 30 minutes? No, it's impossible. So this type of technology is very important, okay, to extend the time of the oxygen tank. So we use the lithium hydroxide to remove carbon dioxide gases from exhaled by the firefighters or astronauts. So and recently uh, I have a chance to write a proposal to get research fund to develop carbon dioxide absorber, better absorber than the other, something like lithium hydroxide. Uh, in order to extend the oxygen tank uh, lifetime, we need to develop even better carbon dioxide absorber. If you have any idea, let me know. We may help the firefighters uh, breathing uh, while they are extinguishing wildfire on top of the mountain, in the middle of the mountain. 2 firefighters passed away. It's very sad. Um, how many grams of carbon dioxide can be absorbed by 1 gram of lithium hydroxide? So we are given the mass of grams of lithium hydroxide. Where is it? 1 gram, right? 1 gram. We have to change this to mole. I have to calculate the mass of grams of CO2. So this is the whole chemical reaction. 2 lithium hydroxide, so solid, plus CO2, then it makes lithium carbonate and water. So 1 gram of lithium hydroxide times the molecular weight, 1 mole lithium hydroxide is 23.95 gram times what's the reaction rate, molar rate, 1, 1, 2, 1, 2, 1, 2, 1, 2, right, 1, 2, 1, 2. 1 over 2 mole ratio CO2 lithium hydroxide times 44.10 gram of CO2 per mole. Then you can get this 0.919 grams CO2. Okay, um, and 18. The most important commercial process for converting nitrogen from air into nitrogen-containing compounds is based on the reaction of nitrogen and hydrogen to form ammonia. Right, it's we can change nitrogen gas to ammonia. The most important commercial process for converting N2 from the air into nitrogen-containing compounds, ammonia gas, is important. How many moles of ammonia can be formed? 3 mole of nitrogen and 6 mole of hydrogen. So let's do this. If we assume one reactant is completely consumed, we can calculate how much of second reactant is needed. By comparing the calculated quantity of the second reactant with the amount available, we can determine which reactant is limiting. I see. Limiting reactant. We have to find what's the limiting reactant. Okay. So the number of moles, let's calculate, of hydrogen needed to complete consumption of 3 mole of nitrogen. Moles of hydrogen. Uh, 3 mole of nitrogen, and this is the ratio of reaction 3 molecular hydrogen react with 1 mole of nitrogen, then we can get 9 mole of hydrogen. We need 9 mole of hydrogen, but we have 6 mole of hydrogen. So 6 mole of hydrogen is available, only 6. So we will run out hydrogen before nitrogen gas is gone, which tells hydrogen is the limiting reactant, right? You understand? Hydrogen is the limiting reactant. So we have to use the quantity of hydrogen to calculate the quantity of ammonia produced. So moles of ammonia, 6 mole of hydrogen, because this is limiting reactant. Okay, we have to use it, not nitrogen. Okay, uh, hydrogen, and 2 to 3 mole ratio of ammonia to hydrogen. Then we can get 4 mole of ammonia, right? So we have to first determine what's the limiting reactant. Okay. 3.19 also limiting reactant. The reaction. I see. We react hydrogen gas and oxygen gas to make water. Is used to produce electricity. This is maybe fuel cell, hydrogen fuel cell. Suppose there might be a catalyst, platinum. Suppose a fuel cell contains 150 gram of hydrogen and 1500 gram of oxygen. How many grams of water can form? So let's first determine the uh, uh, limiting rate. From the balanced equation, we have stoichiometric relations. 2 moles of hydrogen, 1 mole oxygen, 2 mole water. Yes. So what? Using the molar mass of each substance, we calculate the number of moles of each reactant. So we can calculate mole of hydrogen, 150 gram of hydrogen and 1 mole per 2.02 gram. Mm. So 74 mole hydrogen. And mole oxygen, 47 moles of oxygen. The coefficients in the balanced equation indicates the reaction requires 2 mole hydrogen for every 1 mole oxygen. Therefore, all the oxygen to complete react, we should need 2 times 74. 2 times 74 equal 94 mole of hydrogen. Since there are only 74 mole of hydrogen, all of the oxygen cannot react. So what is the limiting reactant? Hydrogen must be the limiting reactant, right? So we use the given quantity of hydrogen, limiting reactant, to calculate the quantity of water, right? We could begin this calculation with the hydrogen mass 150 gram, but we can save a step by starting with the moles of hydrogen, 74, right? 74. 74 hydrogen molecules and the reaction ratio 2 mole 2 and 18 gram water equal 1 mole of water, and then we can get 1.3 times 10 to the 2 gram water. That's it. And what are these? Comment. This comment. 1920. Exercise 20. Adipic acid. Adipic acid used to produce nylon is made commercially by a reaction between cyclohexane and oxygen. This one. A. Assume that you carry out this reaction with 25 gram of cyclohexane and that cyclohexane is the limiting reactant. What is the theoretical yield of adipic acid? Theoretical yield. You have to calculate it. Theoretical yield. And if you attain 33.5 gram adipic acid, what is the percent yield? You remember the equation, simple equation of theoretical yield and percent yield for the reaction. So the chemical reaction was given. So we start the theoretical yield, right? So we know that adipic acid grams, how much is it? 25 gram of cyclohexane here. And then we know the mole weight of cyclohexane. So we can change this to mole first, right? Mole. And then we have a conversion factor of adipic acid and hydrocyclohexane, right? 2, 2, right? So this is conversion factor. And then finally, 1 mole adipic acid is 146 gram. So multiply all those conversion factors and the gram of cyclohexane, we can get the gram of adipic acid, this one, 43.5 gram. This is theoretical yield, right? We can get this. And then what's the percent yield? If you obtain 33.5 gram of adipic acid, then this is theoretical yield, this is actual yield, theoretical gram, and this is actual gram you get product. Then you can do this. Percent yield is actual yield over theoretical yield times 100. So simply this times 177% yield. Good. Okay, it's done of exercise chapter 3. What time is it? It's not 1 p.m. and it's 2:17. Um, we have to, let's see, how many? 37. Don't go away. Okay, don't go away. Let's have a 5 minutes break. 5 minutes break. Uh, this is my hotel room in San Diego. What's the name of this hotel? What's this? Best Western Plus. We want your stay with us to be comfortable. Well, the room is quite comfortable. Single bed. There is a microwave and bath. The very useful thing is bath in the bathroom. Please remember we have complimentary toiletries available if you need them. Just give us a call at the front desk. I have to turn on. Drink something, anything, water or coffee or whatever. Let's see, what should I do? Chapter 3. Right. Did you receive the Did you receive the lecture note 5? Lecture note 5. Where is it? Okay, lecture note 5. We have to jump into the lecture note. Lecture 5, chapter 5. Chapter 5. Hmm. Ch4. What else? The American Chemical Society. There are two general meetings per year, spring meeting and fall meeting. This spring meeting, about 12,000 abstracts were submitted, which means over 12,000 people attended this meeting. And I have seen Professor Nocera from Harvard University today came across in the corridor at the convention center, San Diego Convention Center. He's a very famous guy, and I have met him a few months ago in Japan. Where was it? Hiroshima, yes. We have done the Hiroshima tour. I didn't send the photograph yet. And then I have seen William Goddard from Caltech. So Professor Nocera, and he probably age of 70, and William Goddard is age of 88. Amazing. So the different thing of Korean conference and American conference is senior members join the conference and they participate actively. In Korea, only young scholars. I think most of the attendants are young scholars. Senior scholars doesn't It's not easy to see the sinus colors. And what what else? Uh, okay, chapter 5. Did you open the lecture note? Chapter 5. Uh, we have to finish chapter 5 today. Let's go. We are learning thermodynamics, thermochemistry, not dynamics, chemistry, which means of thermodynamics. Very important. Very, very, very important. Uh, 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 okay. Thermochemistry. Thermo. What is that? Heat. What is the heat? Heat is energy. Right? Very important. Energy. Again, from chapter 1. Energy is the ability to do work or transfer heat. Work or transfer heat. Don't forget it. That's the energy, okay? That's the energy. Energy. If you have energy, you can do work or transfer heat. How can you transfer heat? Uh, that's the energy, right? Definition. Mm. Work equal F force and distance, right? Mm. Uh, and and this F equal ma, right? Mm. So this chapter is about thermodynamics. I'm teaching thermodynamics of uh, material science. So when you are uh, sophomore or third year senior students, then take the class of thermodynamics of material science. Uh, then you can take another course of uh, my mm, lecture. So this chapter about thermodynamics. Thermodynamics. Mm, which is study of energy and its transformation. Energy and dynamics. Transformation. Energy and transformation. That's the thermodynamics. Specifically, thermochemistry is the study of chemical reactions, and the energy changes, reactions and changes that involve heat, reactions and changes. Interesting. Very important. Very, very important chapter. I think most important chapter. Chemical energy is mainly potential energy. Uh, did you remember a person uh, uh, bicycle down to the hill uh, and this person has the potential energy on top of this hill, right? And this potential energy transfer to the kinetic energy, right? Uh, so you may don't understand how and why uh, ionized particles has the potential energy. It is important to understand. So let's see. The graph is you must understand this graph. The most important form of potential energy in molecules is electrostatic potential energy. Electrostatic potential energy. EEL. Electrostatic potential energy. The most important form of potential energy. It has a potential energy. If you let's see. So let's try to understand this graph. Smaller separation, greater repulsion, higher energy, electrostatic energy. So like charges, if they have same charges, these ionized particles or molecules have same charges, then as they close, the repulsion is greater, right? Then the energy is going up, okay? Energy of electrostatic energy is bigger than zero, okay? When they are separated, greater separation, less repulsion, okay? Because they have same charge, lower electrostatic energy. Mm. The equation is simple. Electrostatic energy equal K Q1, this is Q1, and Q2 over distance, right? So this is charged particle, charged molecules, right? So if they have same charge, same like charges, then there are huge repulsion. This is the potential energy. And remember the unit of energy commonly used, the joule. Joule. 1 joule is 1 kilogram meter square over sec square. And the case of opposite charges, right? In this case, the smaller separation, greater attraction, lower electrostatic energy, right? So it's going below down here. Okay. Mm, and this K value is 8.99 times 1 10 to the 9. I'm sorry for this writing. Joule meter per coulomb square. Okay. Mm. This K value is this. Um, and if the separation distance uh, going far, far away, then it's almost zero. So so now you understand the potential energy, right? Mm, let's say then attraction below between ions. Let's go in detail. Mm, let's say okay. I forgot something to say. So K is coefficient, relative coefficient. Okay, 8.99 times 10 to the 9 joule uh, meter per coulomb. Uh, and that's it. Yes. Uh, one charged electron has 1.602176 times 10 to the minus 19 coulomb. Uh, did you remember we have studied it's the charged uh, one electron has 1.602176 and 634 times 10 to the minus 19 coulomb. Hmm. So how did we measure this? Did you remember? Uh, Millikan. Millikan measured this. Uh, this is precise and exactly multiply of these numbers on the each oil droplet uh, in his experiment. So I think the Millikan is the one of the very important scientists. This is the very smallest unit. S uh, we measured. Mm. So one electron, mm, why it has minus charge? Uh, 18th century, Benjamin Franklin uh, defined we have minus electrons. So we have to accept this because the first pioneer defined the electrons have minus charge. Uh, we may we may change it, but we cannot change it. It's 100 years history. So if we change it right now, then we have to change everything. So the first pioneer decided the charged particles, the electrons has negative value. Uh, so that's the Benjamin Franklin. Uh, well, we can blame him, but we cannot change it because historically it is already accepted, and this is agreement among the chemists and physicists. So mm, uh, we have to accept it. That's the difficult way to study this type of Western sciences. But anyway, Benjamin Franklin assigned electron has negative value, and Millikan measure the exact uh, number, the smallest number of uh, charged electron. mm, mm, 1.602176 times 10 to the minus 19 coulomb, right? Coulomb is very smallest SI unit of electron, charged electron. This is Coulomb equal ampere times second. Okay, 1 ampere 1 ampere in 1 second is Coulomb. Coulomb is another scientist. So this is the honorable unit uh, uh, the scientist Coulomb. So, so I do hope you memorize this system. Uh, they have charged particles, uh, and it might be multiply of uh, Coulomb, uh, the value of an electron 1.602 exactly. You must use this uh, term exactly 1.602.176.634 times 10 to the minus 19 Coulomb. Multiple of this number uh, have to use to calculate this type of um, reactions. Okay, that's the history of potential, the beginning of the potential energy calculation. So somebody may ask why it has negative charge, or why it has Coulomb, why it has this number. The scientist Millikan did a great job to measure the multiply of unit um, uh, charge electrons. Okay, uh, so it's amazing. It's really amazing. Uh, so we have to accept it. Um, that's it. And attraction between ions. Attraction between ions. Let's see. Electrostatic attraction is seen between oppositely charged ions. Electrostatic attraction. Uh, oops. Wait a second. Wait a second. International calling. Wait a second. Oops. I'm sorry. Uh, international call. I have to get the phone. Okay. 240. Let's go back to the slide. So this is ionic compounds, right? Electrostatic attraction is seen between oppositely charged ions. Can you see the oppositely charged ion plus minus ions far apart, higher potential energy here. Energy is released when chemical bonds are formed, which means they're stabilized. Energy is consumed when chemical bonds are broken. Energy is consumed when chemical bonds are broken. Okay, we need energy. Ions close together, ion low potential energy. Okay. First law of thermodynamics. Thermodynamics. First law, you have to memorize it. First law, second law, third law. I think there is zero law also. The thermodynamics is very often questioned to the interview, job interview or entrance interview for the grade school. It is very important to memorize the first law of thermodynamics. What's the first law of thermodynamics? Energy can be converted from one to another, but neither created nor destroyed. To heat your home, chemical energy needs to be converted to heat. Sunlight is converted to chemical energy in green plants. There are many more examples of conversion of energy, right? Um, and to understand the thermodynamics, we have to define system and surroundings. System and surroundings. It's not difficult. Uh, if you understand system, then the rest of the system is surroundings. Okay? The portion of the universe that we single out to study is called system. Single out to study. Here, in this case, hydrogen and oxygen, there is probably red color hydrogen as oxygen and white color spheres hydrogen. These molecules are system, okay? And rest of these molecules are surroundings. The cylinders, piston, this piston, and everything beyond, right? Mm. So system and surroundings are what? Uh, Universe. Okay. The summation of system and surroundings are universe. So don't forget it. System is only this one. Hydrogen and oxygen. And types of systems. Open system. There are three different systems. Open system, closed system, isolated system. So let's see. Open system. A region of the universe being studied that can exchange heat and mass with its surroundings. Exchange. Okay? Exchange. Open system. Exchange heat and mass with its surroundings. Heat and mass. Closed system. A region of the universe being studied that can only exchange heat with its surroundings. Exchange heat with its surroundings, not mass. That's closed system. Okay? Isolated system, a region of the universe that cannot exchange heat or mass. Not, not exchange heat or mass with its surroundings. That's isolated system. Then what is this? This is energy can enter or leave the system as heat or as work done on the piston, right? Hmm. But what about mass? Matter cannot enter or leave this system. So this is closed system, right? If we cannot work on this piston or this cylinder, this must be isolated system. But we can do work, transfer heat. So this is the closed system. Okay, this is the closed system. Nothing difficult, right? Mm. Internal energy. What time is it? Internal energy. The internal energy of a system is the sum of all kinetic and potential energy of all components of the system. We use E, large E, to represent it. Internal energy, important, very important. Okay, we generally don't know single energy. Okay, E. We only know its change delta E. So we always have to say delta E, change of energy. That's the internal energy. It's relative value, okay? So loss in this graph, loss of energy from system represented by red arrow, pointing downward from initial state to final state. So we know delta E, okay? The delta, this symbol is change. So we use this triangle symbol and we call this delta E. Uh, uh, And also, given of energy by system represented by blue arrow pointing upward from initial state to the final state. This is also delta E, right? So in this red case, energy lots of surroundings, energy lost to the surroundings. So the initial energy inside the cylinder uh, lost to the surroundings. Internal energy of the system decreased. Delta E negative, right? Mm. Decreased. And energy gained from the surroundings. Internal energy of the system increased. So delta E is positive, right? Hmm. Nothing difficult. Change of energy, internal energy, right? Uh, so by definition, important. Do not ask me. This is definition, right? Definition by the senior scientist. From this definition, we apply many questions, okay, to solve the questions. The change in any internal energy, the change in internal energy, delta E, is the final energy of the system minus the initial energy of the system, right? Simply. That E is E final minus E initial. So for example, initial state, we have hydrogen gas and oxygen gas, initial gas, okay? And what we get, low temperature, water, right? So the final state is even lower than the initial state, right? Uh, the internal initial energy greater than final energy. Therefore, energy is released. Energy is released. Energy is released from system to surroundings during reaction, right? So delta E is smaller than zero. And if delta E is positive, then E final should be bigger than E initial. The system absorbed, very important word, absorbed energy from the surroundings, okay? So the final state of the system is higher than the initial state. Then delta E is positive, positive. This system released, oh, sorry. When if delta E is negative, I told you, negative, the system released the energy to the surroundings, right? Uh, if initial energy, change in initial energy is positive, then absorbed the energy, release the energy. Thermodynamic quantities have three parts. Memorize it. Thermodynamic quantities have three parts. Room is cold. Excuse me, I want to wear wear something. Oh, wait a second. Okay, I want to wear something. That's cold. Okay. Three parts. Number, number. Units. Units important. When you take midterm exam, if you do mistake of units, then that's wrong answer. Okay. Even though number is correct, if you did mistake of units or sign, okay, one of these three, if you did mistake, that's wrong. Okay, that's wrong answer. Okay, do not complain anything. You must check number, unit, sign, all three things. Okay, very important. Very, very important. Even if you completely good calculation of all those questions, I don't care. If you did wrong unit, wrong sign, then that's the wrong answer. Okay, because you are a undergraduate student, not a high school student. So all those three things very important to solve the questions. Note about sign. A positive delta E result when the system gains energy from the surroundings. A negative delta E results when the system loses energy to the surroundings. So the sign is important. Okay, sign is important. Sign. So if you don't understand, remember this safe diagram. You know the illustrate of safe. Uh, work done on the system, heat gained. Okay, Q equal positive, Q positive, work positive. Then energy deposited into the system. Then what? Delta E, change of initial energy, positive. Heat lost, work done by the system. Work done by the system. Then energy withdrawn from the system. Energy withdrawn from the system. Then delta E, negative. When energy is exchanged between the system and the surrounding, it is exchanged either heat or work. So delta E, we can describe delta E Q plus W. This is very important. Change of internal energy is related to either heat or work. Okay, it's very important. This is thermodynamics. Okay, thermodynamics, right? Um, so if you memorize this illustration, then you don't need to be confused. Let's see. Delta EQW, their signs. This is the table. Uh, for Q, positive means system gains heat. Okay, minus means system loses heat. Work, positive means work done on system. Negative means work done by systems. Net gain, net gain of energy by system. Negative means net loss of energy by system. Okay? Mm. So exchange of heat between system and surroundings. When heat is absorbed by the system from the surroundings, the process is endothermic. Great word, endothermic. Endothermic. So let's use what is this? Let's use ammonium cyanate, ammonium cyanate plus barium hydroxide, 8 water. Mm. This is the system. We use two different chemicals, right? Um, Barium hydroxide water plus 2 ammonium thiocyanate. Let's react those two things. Then it makes exchange reaction barium thiocyanate. Thio means sulfur, okay? Barium thiocyanate plus ammonia and water. Okay, this is endothermic. Look at this. 23 degrees Celsius room temperature changed what? Minus 11. What happens? Heat flows from surroundings into the systems. Temperature of the beaker and surrounding air drops. Temperature of beaker and surrounding air drops. Temperature of beaker. Temperature drops. Right? Temperature drops. What does that mean? Observe the energy from the surroundings. Okay? So we use this uh, commercially uh, for the athletics when they have burn on their muscles, something happened on their uh, bones, then they use cold pack. Uh, they use this one. So this is endothermic reaction. When heat is absorbed by the system, okay, and when heat is released by the system into the surroundings, the process is exothermic. Exothermic. What is this? This is potassium. Potassium. Very active metal. Potassium and water. Don't do this. Never ever. Okay? Lithium, potassium. Very active material. So somebody drop the potassium metal, piece of metal into the water. Okay? Then what happened? Heat flows violently from system into surroundings. Temperature of the water and surrounding air increases. Temperature of the water and surrounding air increases. Right. So when you do this type of experiment in the lab, you must be very careful. Okay, very careful. State functions. State functions. Usually, we have no way of knowing the internal energy of a system. Finding that value is simply too complex a problem. However, we do know the internal energy of a system is independent of paths by which the state achieved that state. the system achieved that state. In the system below, the water could have reached room temperature from either direction. Let's see. 50 gram of water, 0 degrees Celsius, ice warms up to water, 25 room temperature. Once this temperature is reached, the system has internal energy. Yes. And then this amount of water, initially hot water, cools to water to 50 degrees, 25 degrees Celsius. Once this temperature is reached, system has internal energy from hot water to this and cold water to this. Usually we have no way of knowing the internal energy of a system. Finding that value is simply too complex a problem. We do know that the internal energy of a system is independent of the path by which the system achieved that system. We call this state function. Another word, therefore, initial energy is a state function. Initial energy is a state function, which means it depends only on the present state of the system. Okay, state function is depends on the present state of the system, not on the path by which the system arrived at that state. And so delta E depends on energy initial and energy final. So we just trust the initial state and final state. We don't care about what happened. Okay, what happened from here. Uh, Sorry, this is the initial state, both initial state and final state. Okay, we don't care about the what happened in between this initial state and final state, right? So we don't care about the path. Okay, not on the path by which the system arrived at the state. Um, that's the state function. So here is an example of a state function. To understand what the state function is, let's say Q, heat, and W are not state function. Okay, now let's see. Delta E was Q plus W, right? This is a state function, but Q, heat, and work is not state function, right? Whether the battery is shorted out or is discharged by running the fan, its delta E is the same. So we don't care about the path, right? But the Q and W are different in the two cases, right? So where is charge the battery here? Okay, charge the battery here. This is shorted out. Okay, energy loss only as a hit, only as a hit, right? Energy loss. We have discharged the battery. We know delta E, energy loss by battery. Okay, this is state function. We don't care about the path of the energy loss, right? So this is delta E, state function, right? So in the case of the battery is shorted out, then it generates heat, okay? Only heat, okay? So energy loss only as a heat. But in the case of running a fan, okay, energy loss as both heat and work. What does the meaning of heat? If you touch this part, it's warm, okay? And the fan running circle, right? So this is heat plus work. Q plus work. Okay, so this is not a state function. Well, so Q and W are different in the two cases. Okay, do you understand? The illustration explain uh, as easy as possible to understand. So if you are confused, memorize uh, memorize the whole illustration to understand what's the state function. Okay, so the energy change from initial to final, the internal energy change of internal energy is the state function. Okay, state function energy loss by the battery delta E. Okay, always the same, but uh, the way of energy loss only as heat uh, or work, heat and work. We can arrive to the discharge the battery energy state, energy level. So these are not the state function. They have different uh, cases. Heat only, heat plus work. Then what is work? What is work? Okay, what is work? What time is it? 11:08. 아이고. Work. Usually, the only work done by chemical or physical change is the mechanical work associated with a change in volume of gas. Let's divide this sentence into two parts. Usually, the only work done by chemical or physical change is the mechanical work associated with a change in volume of gas. So let's see this illustration. Um, so system does work. This system does work W minus P delta V on surroundings as gas expands, pushing the piston up distance delta H. Where is delta H? Delta H. Okay. And the area, cross-sectional area A. Right? This is what? Delta H times A. This is what? Volume, delta V. Volume change. So work, system does work to change the volume, right? This amount of volume. And so this is the work. P. So we know the change volume and P equal the work minus. Surround does work, so a system does work on surroundings. On surroundings. Okay. As gas expands, pushing piston up, distance delta H. So this is initial state and final state. And gas enclosed in the system. This is the closed system. So let's what's the detail of this system is, this experimental is. So work We can measure the work done by the gas if the reaction is done in a vessel that has been fitted with a piston W equal minus P delta V. The work is negative because it is work done by the system, right? Mm. So let's look at this illustration of experiment. Zinc sulfur, no, zinc, solid zinc metal. It might be powder. Okay. Let's turn this cork opposite side. Then the zinc powder, metal powder, goes into this uh, hydrochloric acid. Then what happens? It generates hydrogen gas. Look at these hydrogen gas bubbles. Okay, then the original place of piston is going up. What is this? Delta H, right? Cross-sectional area A, right? So the volume V equal A times delta H, right? Mm. This amount of work done by what? System. By system. So it is increase in volume means the system does pressure volume work. So this work is negative. Negative. Hmm. Okay, so we have studied state function, uh, delta E, described Q plus W, right? Internal energy is uh, state function, but Q and W are not state function. And enthalpy, very important, enthalpy. If a process takes place at constant pressure, and we usually work at atmospheric pressure, and the only work done is this pressure volume work, pressure volume work, we can account for heat flow during the process by measuring the enthalpy. Here is this. Heat flow, heat flow during the process, heat flow by measuring the enthalpy of the system, enthalpy of the system. Uh, that is, enthalpy is the internal energy, plus product of pressure and volume, product of pressure and volume. So enthalpy is E, internal energy, plus pressure and volume, product, pressure and volume, product. That's the enthalpy definition. If a process takes place at constant pressure, because we usually work at atmospheric pressure. Okay, it's not less. I think very rare case on the different pressures. Most of the work at atmospheric pressure, so we use constant pressure, and the only work done is the pressure volume work. So we can account for heat flow during the process by measuring the enthalpy of the system. Heat flow, uh, enthalpy, is the internal energy plus the product of pressure and volume. So the enthalpy when the system changes at constant pressure the change in enthalpy, delta H, is this. And this can be written as this. I said P is constant because we are usually work under atmospheric pressure, right? So the enthalpy is change of internal energy and change of volume, right? This is the enthalpy. Measuring heat flow we can account for heat flow. Oops. Mm. So since delta E internal energy equal Q plus work and W work equal minus P delta V, we can substitute these into enthalpy expression delta E delta H enthalpy equal delta E plus P delta V, and we put um, this one this one into here, then you can get this, and delta H equal Q. So at constant pressure, the change in enthalpy is heat gained or lost. Heat gained or lost at constant pressure. Okay, at constant pressure, right? Mm. So in order to understand this mechanism concept, we need to use another illustration. So constant pressure maintained in system, heat gained delta H should be positive, which is endothermic reaction. Okay, heat loss, the delta H enthalpy is negative. An exothermic reaction, delta H is amount of heat that flows into or out of system under constant pressure. So process is endothermic when delta H is positive. Endothermic process is exothermic when delta H is negative. Exothermic. Exothermic. Lose of temperature. Mm. Enthalpy reaction. Example. The change in enthalpy delta H is the enthalpy of the products minus the enthalpy of the reactants. This one. Okay. Delta H reaction equal delta H products minus delta H reactants. Uh, let's say, let's see. This is reactants. We burn methane gas with oxygen. Then what happened? This is exothermic reaction. Heat, carbon dioxide, and water, and release heat energy. Right? So it is negative. What is that? Delta H negative, exothermic reaction. Okay. Uh, so, well, recently my research group is working on carbon dioxide conversion to hydrocarbon fuels, right? So even though the carbon dioxide is the very final product and stable molecules, we may give energy. What energy? And what? Energy and catalyst. Okay? If we have a photocatalyst, for example, photocatalyst, photocatalyst, and the photons hit photons, uh, then what? We can reduce carbon dioxide into methanes, all right? Uh, we add energies into this system. Okay, this is the reactants in this case. Then the product is methane gas and oxygen gas. So we add this amount of heat energy, delta H, heat transfer, right? So it is what? Endothermic reaction. Endothermic reaction. Delta H positive. Mm, enthalpy of reaction, delta H R reaction is called the enthalpy of reaction or the heat of reaction. So what is this? In a volume, this is not that safe experiment in a volume. Somebody added hydrogen gas and oxygen gas, uh, very flammable hydrogen gas. And then explosion and flame indicate system releases heat to surroundings. Then what is this? This is ectothermic. This is reactant. We have only hydrogen and oxygen. If there is any spark or small flame, as like here, or spark, it explode, okay, uh, immediately, and a lot of energy released, which is exothermic, and delta H should be negative, and the final product is water. Okay. Hmm. Violent. So the truth about enthalpy. What is the truth of enthalpy? Enthalpy is an extensive property. Extensive property. Extensive property. Extensive property. Memorize it. Enthalpy is extensive property. The enthalpy change for a reaction is equal in magnitude, but opposite in sign to delta H for the reverse reaction. The enthalpy change for a reaction depends on the states of the reactants and the products. Okay? The truth about the enthalpy. Memorize it. The enthalpy is an extensive property. Okay? The enthalpy change for a reaction is equal in magnitude. Magnitude is extensive properties, magnitude, but opposite in sign to delta H for the reverse reaction. The enthalpy change for a reaction depends on the states of the reactants and products. Colorimetry. 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 Oh my god. We have still a lot of slides. Oh my god. Colorimetry. Since we cannot know the exact enthalpy of the reactants and products, we have to measure change of enthalpy through colorimetry. So this simple experiment is very important, the measurement of heat flow, right? Colorimetry. I think you may do this experiment in the general chemistry experiment class. The instrument used to measure the heat flow is called colorimeter. What is this composed of? Thermometer, glass stirrer, cork stopper, two styrofoam cups nested together. Okay. and reaction mixture in solution. All right. Heat capacity. We must understand the heat capacity and specific heat. Okay, to do this experiment. All right. Heat capacity. The amount of energy required to raise the temperature of a substance by 1 Kelvin is the heat capacity definition. Okay, the amount of energy required to raise the temperature of a substance by 1 Kelvin. If the amount of substance heated is 1 gram, it is specific heat. Specific heat. If the amount is 1 mole, it is molar heat capacity. Mm, Nothing difficult. Memorize it. Definition. Okay. Mm, Specific heat some substances at 298 Kelvin. Mm, What? The specific heat of water is the very big, 4.18 joule per gram Kelvin. Uh, Memorize it. Um, then constant pressure calorimetry. By carrying out a reaction in aqueous solution in a sample calorimeter, the heat change for the system can be found by measuring the heat change for the water in the calorimeter. Of course, the specific heat we already know for the water is 4.184 joule per gram Kelvin. We use this value for dilute solution. Okay, so we can calculate delta H for the reaction with the equation Q uh, Celsius mole times delta T. Mm, C is heat capacity. Where is the heat capacity? Heat. C is heat capacity. And M is molar heat capacity. Okay. And T is mole solution. Q solution. Delta T equal minus Q reaction. Uh, Capacity, mole solution, capacity. Uh, I think this is mass, mass of solution. Capacity. This is specific heat, specific heat and mass of solution and temperature. Okay, sorry, I changed this. Specific heat, and mass of solution times delta T, temperature change, equal minus Q reaction. This is calculation of delta H for the reaction with this equation. Uh, again, C is specific heat, specific heat, mass of solution, change of temperature equal minus Q reaction. Okay. Uh, right. Okay. Then bomb calorimetry. Reactions can be carried out in the sealed bomb, such as this one. I don't know why they like to use bomb, but it is bomb calorimetry. The heat absorbed or released by the water is a very good approximation of the enthalpy change for the reaction. Okay. So Q equal minus C times uh, temperature change. Mm, okay. Uh, the heat absorbed or released by the water is a very good approximation of the enthalpy change for the reaction. So it has minus, we can see stirrer here, sample ignition wires, sample ignition wire IC, thermometer. I think why they call this a bomb. There is some bomb reaction chamber. This is bomb reaction chamber. Okay, insulated container. Insulate the container. We can ignite this uh, sample, and then we can uh, see the temperature change by this reaction. Then we can measure the temperature. Then we can calculate the Q reaction. Okay. Mm. It's different from the general colorimetry. Okay, and because the volume of the bomb colorimeter is constant, yes, that is measured. What is measured is really the change in internal energy, delta H. No, sorry, delta E, not delta H. For most reactions, the difference is very small. Delta H is well known for many reactions, and it is inconvenient to measure delta H for every reaction in which we are interested. However, we calculate change of enthalpy using published delta H values and properties of enthalpy. That's Hess law. Hess law. Hess law is if a reaction is carried out in a series of steps, delta H for the overall reaction equals the sum of the enthalpy changes for the individual steps. Hess law. Memorize it. Hess law. Because H is a state function, H is a state function for a particular set of reactants and products, delta H is the same whether the reaction takes place in one step or in the series of steps. Let's see. So this is the enthalpy change from oxidation of burning methane gas with oxygen. There might be a two-step reaction, uh, but it is the change of enthalpy, we summation these two values is same as this one, right? So the enthalpy formation, that's the Hess law, okay? Uh, if the reaction carried out a series of steps, it's like this methane oxidation. Delta H for the overall reaction equals the summation of enthalpy change for the individual steps. We have individual two different steps. Now, one additional step, okay, from here to this and here to this. Okay, what else? So the delta H is also state function, right? So it doesn't matter about the path uh, of these steps uh, in both sides. So delta H is also state function. Enthalpies of formation. An enthalpy formation, delta HF, is defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental forms. What does this mean? Let's go. Standard enthalpies of formation. Our senior uh, scientists measure all these standard enthalpies of formation are measured under standard conditions 25 degrees Celsius and 1 atmospheric pressure. Okay, so you have to know how to use this standard enthalpy of formation. Right? Anything interesting things? We may use this table later. Okay, calculate delta H. Propane gas burned under oxygen, we may get CO2 gas and water. We can find the standard enthalpy formation in this table, right? Propane, where is propane? Propane here. Okay, we use this value and water this, and oxygen, no oxygen here. CO2, okay, doesn't matter. Imagine this is occurring in three steps. First, decomposition of propane to elements, three graphites and hydrogen. Reaction, propane and oxygen goes up to three graphite and hydrogen and oxygen, and going down. Formation, three CO2, hydrogen and oxygen, and going down finally, carbon dioxide and water. This is the final product. So we may have three steps: one, two, delta H, delta H2, delta H3, three steps, or delta H, I see. By using this one, we can calculate the standard reaction uh, enthalpy, minus 2220 kilojoule. So we consider the second formation of CO2 and third formation of water. And so all steps look like this: one, two, three. Uh, and then the summation of these equations is the overall equation. Yes. And then we can use Hess law in this way. Then delta H is a summation of n, number of moles of delta H5F products, and minus delta M, sorry, not M, delta HF standard reactants, and then M are the stoichiometric coefficients. Okay. Then let's this. You add all the standard coefficients, sorry, stoichiometric coefficients of these chemical reactions, and uh, the delta H values. You add all the delta H values, and then you finally get this number, delta H minus 2220 kilojoule. That's the calculation of delta H using values from standard enthalpy table, right? Okay. Bond enthalpy. The enthalpy associated with breaking one mole of particular bond in a gaseous substance. So the bond enthalpy is always positive because energy is required to break chemical bonds, right? Energy is always released when a bond forms between gaseous fragments. The greater the bond enthalpy, the stronger the bond. So our senior scientists already measured the average bond enthalpy is a kilojoule per mole, right? So you have to use this table, okay, to solve those questions. Bond enthalpies and enthalpy of reaction. Add bond energy to all bonds made positive. Subtract bond energy for all bonds broken negative. The result is an estimate of delta H. So delta H reaction equals summation bond enthalpies of bonds broken minus summation bond enthalpies of bonds formed. Bond enthalpies and enthalpy of reaction. So we can predict whether a chemical reaction will be endothermic or exothermic using bond energies. It's important. We can predict, okay, endothermic or exothermic. Methane here and oxygen. We burn the methane with oxygen. And delta H positive break CH bond and sorry, this is dichloride. Okay, not oxygen, dichloride. And delta H1 positive. And one hydrogen is broken away from the methane. So this might be methyl radical. And chlorine is also broken, chlorine ions. Then it makes carbon chlorine and hydrochloric acid bonds. So delta H negative. And we found methyl chloride and hydrochloric acid. So we can calculate delta H reaction by using uh, uh, bond enthalpy, right? Uh, Energy in foods. The energy released when 1 gram of food is combusted is its fuel value. Ah, a lot of compositions and fuel values of some common foods. Carbohydrate, approximate composition 100, fats 100, fuel value. Okay. Mm. Energy in food. Most of the energy in foods comes from carbohydrates, fats, and proteins. Carbohydrates 17 kilojoule per gram. Glucose, representative. Burn with oxygen minus 2,803 kilojoule. Fats 38 kilojoule per mole. Ah. Protein produces 17 kilojoule gram, same as carbohydrate. Their chemical reaction in the body is not the same as in calorimeter. Mm, Energy in fuels, let's say, uh, fuel values and compositions of some common fuels. The vast majority of the energy consumed in this country is USA, comes from fossil fuel. How much? Natural gas, coal, uh, renewable energy, petroleum, natural gas, coal. Vast majority of the energy consumed in the States comes from fossil fuels. A lot of global warming gas coming out. Other energy source, nuclear fission, Only less than 10%. Amazing. Less than 10% of the United States energy needs. Where is it? Nuclear. All right. It's going to be increasing. Renewable energy source also less than 10%. Very low. Very low. Renewable energy. Uh, okay. This is the end of the chapter 5. Right. Thank you very much. Um, thank you very much. Oops, where is it? All right. Uh, it's 3:47. Uh, some of you left. I don't know. Thank you very much for joining this live streaming, and I do hope you understood the thermodynamics, which is important. And I would like to see you on next Tuesday in the class to study some exercise of chapter 5 and 4. We did 4, right? 4. Okay, we should do. And then, hmm, okay. I'll see you next week. Bye bye. 댓글 김민성 댓글 봤어. PDF 우하단이 가려서 잘 안 보인다고? 아, 그랬어? 그랬구나. 음. 그 출석했다는 얘기지 댓글 한번 봐주실 수 있냐는 얘기가. 출석 확인했어요. 아, 그렇지. 안원 형이 나와서 출석했습니다. 다 했지? 출석 안 하면 안 돼요. 그렇지. 이니셜 쓰지 말고 이름을 쓰라고 아까 그랬는데. 오케이. 아이고. 3시간을 열심히 달렸더니 힘드네. 그러면 이걸 끄겠습니다. End of string. 오케이. Bye. Bye.